Hi everyone, good morning. Hi Nikita, can you hear me?
Yeah, I can hear you.
Yeah, apologies, I was trying to troubleshoot something on my PC.
Yeah, it's
Okay,
okay.
good morning everyone. Thanks again for joining us today. In week 5, today we'll be talking about time series in astronomy, and Nikita will be leading the presentation for today. Just a heads up, for those who did not join um, the lecture last week. Please, we've kickstarted project for, I hope you guys are working on your project. If you have any question, please ask in the Slack channel. We'll open up the web link for submission next week. The link will be provided starting next week for the submission for those who have done their projects, and then it will end towards the end of week 8. So please start working on your project as quickly as possible. All right, Nikita, you can go ahead.
Okay. Is my screen visible? Can anyone confirm?
Yes, we can see
Daniel?
this. Yes.
Okay. So hi everyone, I am Nikita and I am a postdoctoral at South African Astronomical Observatory, and today in this week I will handle time series data and how to handle time series data with Python. So as we talk about time series data, so the first question arises, what is time and how do we define time in Python? So if you talk about time, you see, uh, we whenever we say time, we measure some changes and events that occur in a course of events. So, like in a global standard form, we use universal time coordinates, which is called UTC, and the universal time coordinate is it's also a reference point so that we can measure something from a reference frame. So you see, so we all are attending this meeting from different time zones. So because the reason is because every country, it has its own local time, and that local time is an offset from the UTC. So, but in astronomy, we don't rely on this UTC format, and I will cover in my later notebooks that how we define time in astronomical observations and dataset. So today I will discuss 3 notebooks, and the first one is just based on the time. In the second notebook, I will discuss what is the time domain astronomy, and in the third notebook, this is specifically to use and analyze test data or Kepler or K2 data from a specific Python package, which is known as LightCarve. So you see, Python's standard libraries include 2 modules, date, time, and time, where we have to function and where we have to calculate any duration or any type of, like, duration means the difference between the 2 time events, and we use date, time, and time for this purpose. So here you can see it just okay, so we have just imported our datetime package from Astropy, and if you will call if you call datetime, and inside that if you call datetime.now, so it will give you the current moment. And I am pretty sure if you try this now, so you will see we have, because I am attending from South Africa and someone is from India, someone is from Brazil, so you might get different answers here if you run this cell right now. So you can also specify based on the current moment, which we have defined here as datetime.now. You can also call the local time, which will be the the standard UTC time. It's the year, month, and date, and then it's hour, minute, and seconds. So you can call these individual entries by calling individual thing. Like if you call just current moment dot year, you will be able to know the year of that moment, and in the same way you can call month, day, hour, minute, and anything. Like you can also call here seconds and then nanoseconds. Now this now we will see how you can create, like if you have any specific date and you want to create that as a Python object, as a Astropy object. So you have to just call date time, and you can define your year and then month and day, and then it will be like hour, minute, and seconds. So for example, this is the date for the first detection of a gravitational wave event, and it's known as GW150914. And this is also visible here that, so in astronomy, some of the events, they are particularly tied with the date in which they are observed. So here you can also identify that this GW event, it happened on 14th of September in 2015, which is also in the, like it's embedded in its name. So if you have defined your event date as in this manner, so you can call this object, and you can print, and you will see that it will give you, so it will give you the specific event time which you have already described here. And similar manner, you can also just create a date if you don't want to, like see, if you don't have any information about time, or if you're only interested in date, so you can also specify these date as well. So in astronomy, whenever we talk about time series data or the time domain astronomy, the time factor is very, very important. It's because, so it's like, so suppose you have you are interested in measuring the temperature over a week, so you started on Monday, and you noted down, okay, Monday at 9 a.m. you have this temperature. Then again on Tuesday you uh, you whatever instrument you were using, or maybe you were just using your cell phones. So on Tuesday you also made a list, and you noted down the temperature. And in this way, suppose you have a series of days which are from Monday to then again Sunday, and the different temperatures. And suppose you have, so that you, in that week's time, you have different temperatures. So if the temperature range is, let's say, suppose 30 degrees Celsius to 40 degrees Celsius, so that means that the variability uh, in this type of light curve is 10 degrees Celsius. And because you have information of day of the week, so you can say that, okay, that first you can put Monday as your first day, and you can write it down as 1, and then the consecutive days you can write 2, 3, 4, 5, 6, 7, and in that way your time column will include the days of your weeks, and your variability value will be the temperature. So but this is how you can understand the in your daily life, how you can understand the time series and the time concept. But in astronomy, since we are not interested in this, I mean the universal time coordinates, and I will talk about something interesting in my second time domain, in the second notebook. But for now, you can see, using this date time library, you can, so if you want to know the duration of your two events, so suppose you started on Monday, and then again the last temperature reading was done on Sunday. So you can mention, okay, you started on, let's say today is 11, you started on 11, and the time 2 will, let's say it's 17. So you can define these two different time events, and you can define a duration which will be just a difference between these two time duration. And just if you use the print command, I hope you are familiar with these commands now. So you can say that, okay, what would be the total duration? Here we have defined our first observations as random date as 15/11/2023, and the hour minute, we have defined our hour minute second as 10:00, and the second time we are interested in the same date, but it's just the difference in minute units. So you see, if I run this cell, I will get something like the time difference, the difference is duration is 30 minutes. But if you like to see this duration in seconds, so you don't have to do anything very complicated thing. You can just say that, okay, this duration, you want to see it in seconds, but because I mean that you can define that this total duration in seconds, and when you divide it by 60, so you will get the duration in minutes. So that's what we are saying here, that the total duration in minutes is 30. So suppose if you want to check whether you have any unique dat, and whether that unique dat it falls in a particular window. So let's say our start window here starts at 9 o'clock, and then the end window it goes to 11 o'clock. And if you want to see whether your time one, which is like a 10 o'clock, whether it falls in this range within the start and end window range, so you can just use this command and see. Here we have already only defined the, we have just stated here that, okay, if my time one is within this range, and since it is, so it will just say that, okay, this is true. So you can do all this stuff, like you can make a random time, time event, and you can do the you can calculate its duration. And the duration is particularly important in astronomy because it depends on which type of astronomical object you are working with. And for some objects, it's very important to observe a particular target for a longer duration of time, so that we can infer its physical properties using that light curve data. So now here, till now, so our we have just created an event date. I mean, our whatever date format we had till now, it was just an object time. But now we want to convert all these columns which have these timestamps into a date time format, so that the Astropy can so that our pandas know that, okay, it's already in time format. So suppose we are creating a simple data frame in which like our X values or whatever, here we have called it as event IDs. So these are 4 different IDs, and these are our time values, which are like, it's just that different days and different times, and these are the values. So suppose it's like we have these timestamp string as the weeks, like as I said, let's say today is 11th June and that is Wednesday, then 12th of June, which would be Thursday, and the different times. And here in the value, suppose you have the temperature values. But now we want to make this event data as a simple data frame, which we can read using pandas. So what we will do, we will first define the individual event, I mean, it's just event IDs are just the serial numbers. So these are our serial numbers, these are our times strings, and these are our respective values in which we are interested. So if you run this cell, you will see, we will see something like that. So this is the data frame which we have created here, and it will give you the individual information. And if you want to call the individual data, you can also call it like using the indexing. So if you write event df 0, you will see it will just give you a first first row. So here you see this was all the information which we had provided, and we can see it's in a nice tabular form. Now we would like to see, so what type of whether the data type is object or what. But because we just started with creating a data frame, so they must all have their respective mm, data types. So because this is all integer, so the event IDs are all integer values, the timestamp string, because we have defined in this manner that, okay, this is our date and this is just an hour, so it is still an object. Still an object, but here we want to make sure that our data frame knows that the timestamps, they are the time, they are the time values, not just an object time. So what will we do? So we will use this function of pandas, and we will call it as pd.datetime to make sure that our data type, it changes from object to a timestamp value. So if you run this cell, you will see that, okay, we have just printed the data types after conversion, and you will see that now our event ID and values, they haven't changed, but the timestamp string is now in a standard date time format, which is date time 64 for pandas, and in the bracket it's written ns, which is nanosecond. So it tells you that, okay, so the whatever time it has stored in the data frame, it is done with the nanosecond frequency. So now we have our column in which the timestamp string is in the dates time 64 format. So we can easily call this timestamp using the time format, and we can do all the arithmetic operations. Like if you want to use not the arithmetic, I mean the comparison operators, we can use those operators to decide whether whether any event that has been observed before or after, or whether they are observed on the same date. So okay, so this is the same old data frame, and but now here these all data. So now this data frame knows that, okay, this one, this second column, which is the timestamp string, is the time we are talking about. So let's say we start on a random date, and we say that, okay, we want to filter data based on whatever in whatever part we are interested in. So let's say that the starting point is this date, and our end is something like, so we want to see all the data points which have happened on this date or after this date. So we can just call this timestamp string here, because now we have defined that this timestamp string is a time form, is containing time, and it is denoted by the time thing. So we can just call this timestamp string here, and we can argue that, okay, I want all the data, which is here you can see we have used the comparison operator, which is greater than equal to. So I'm just calling all the events which have happened on this date, whatever filter start date I have provided, and after after this filter start date. So if I run this cell, you see it will give me all the data. So here, because the filter start date is 6/1/2023, so it will give me data on of this date and the second, the after that, and the last date of 8th of January 2023. Now we can also specify a particular. So here we had only specified the date, but you can use the same thing to to filter out based on the uh, time as well. So in the second example, we have just the start, whatever the start range is in date, but in the end range, we are interested that it doesn't go beyond this specific time. So, and based on the simple comparison operators, we can use the data frame and filter events based on the whatever information we need for our science cases or for whatever case. Now, since now our data frame knows that these timestamp strings these are like the time values, so we can also set these timestamp string as the index of the um, uh, index of the data frame. So it's like, because you see, whenever I have talked about the time series data, I have said that the first column, whatever the first column we have, it's the time we have in the first column, and in the second column, I only have the y value, which could be anything, like in temperature in our case. So now we want to see our data where we can just uh, whether we can just call our data based on its timestamp string. So here we have defined, here we have said that we have used our data frame and we have just used a simple command which is set index. And when you run this command, it will make sure that now all the time, so all in the first column, these are indexed as 0, 1, 2, 3. So now if you call as, like if you call 0th index here, it will give you this time, and similarly so on for the other data frame values. So now we know that our data frame has this information. It has information that, okay, they have different index now. So we can also filter our data, or we can also slice our data set based on the individual values. So if we use this, our new data frame, which is indexed now, so and if you want to slice using just these, like in these data set, so you can just run it, and wait just a second. It should slice by. Okay, yeah, here we go. So yeah, so we have denoted here two dates, and we have just used our initial data frame, which is indexed now. And if you so we want to see like the data which are from this date to this date, so we can just slice using the index values now. So you see now it has just taken this information from the data frame, and it has given you its corresponding event ID and its corresponding y values. Similarly, you can do the similar stuff for for an individual entry. So here we were just interested in this entry, which was the third entry from the from our data frame, and we have just picked up this using the LOC using the LOC, just the data frame.lsc. We have just used this for label based indexing. So if you run this, you will see, you will get this, the individual entry for this date and its corresponding event ID and its value. So this is just a normal stuff which this you can also use for in your everyday's life, where like if you want to make a log of everything, so you can use all these routines to make a log, or suppose we are observing and we want to make sure that okay, which observations and what done at what time, so we can make a script using these all routines and we can run that. Now we will move forward with time domain uh, time domain astronomy. So interestingly, so whenever we say that an astronomer observes anything in the sky, we generally, what we measure, we generally use our telescope and point it to a target, and we observe its light and whatever radiation comes from that particular object. But nowadays, so astronomers are really interested to see what are the changes which are happening over over the time in sky. And this field is known as the time domain astronomy, where you measure a large field of view, where you measure a large patch of sky and you observe that sky for, let's say, whatever, depending on the science goal. So you measure that, let's say, for 10 minutes, and then you come again tomorrow and then you measure again. So this type of observation mode is called the survey mode, in which you continuously observe a large field of view of a large patch of sky, and you see if there are any changes which have happened from the previous observations. And in this way you can also get a sense of like what things are so what are the objects which are variable, and what are the objects which are, I mean, the constant one and non-variable. So the sources which are variable, so they also depend, I mean, the kind of variability, it depends on the physical processes which are driving them. And so, even the time duration of different objects, it could be different. So we have something called pulsars, and for them the duration of this variability is millisecond. And we also have solar cycles, in which so sun, the nearest star, it also has its own cycle, in which the number of sunspots in sun, they change on a time scale of years. It's probably 12 years or something. So, and I mean, you can read here, it's all about how we have the current survey telescope, we have its Juki transient facility, and the upcoming LSST will be a stepping stone in this process, where it will observe southern sky in survey mode. So in this notebook, you will understand how a time series data looks like, and how, I mean, you can call it. And if suppose some data is already published and you want to see and explore that data, you can we will see how you can call them. So so I will not go into these details, but I will just want to let you know that, okay, what are the key terms which we use when we talk about time domain astronomy and time series data. So a time series data, as I explained before, it's like you are measuring something, and that something could be any property. In case of astronomer, it's most of the time it's its brightness, but some of the time it could be its position and its velocity. And we measure that particular property for a longer duration, for and at a consecutive time. So and whatever data we get in this way, like if we have time and we have the respective y value, I mean respective whatever property we were interested in. So let's suppose brightness for here. So if we're interested in that kind of data, so we have time in axis and we have brightness in y axis, and if you plot this, so it will show you some kind of variability, and that is known as the time series data. And the time domain astronomy, it's the that branch of astronomy that deals with these changes, and these changes include any kind of variable stars, the supernova explosions, gamma ray burst, and active galactic nuclei flare, and exoplanet. And the light curve, as I just mentioned, that it's just a plot between the time and y value, which could be like brightness or flux or even the velocity. And a transient, so a transient is a short-lived event in a sky, and so whenever we say that a particular target or source is a transient, so we are interested in its duration. So what happens is it just appears, and it just appears, and then its brightness it changes significantly, and then then it just disappears. And these type of objects, which are known as transients, they include supernovae, gamma ray bursts, and stellar flares. Now, so whenever we talk about light curve, so it's either a flux or a magnitude. So flux is like it's a physical measure of whatever radiation we are getting from an astronomical source, but it also because we are getting it from a celestial source, so it's like per unit area. And the magnitude is just the magnitude is basically a flux, but it's noted in the logarithmic scale. And so most of the time we are in a light curve data series analysis, we are interested in either in flux or a magnitude. And okay, so epoch is just a specific point in time. Suppose you have a binary star, and they are like, and the one star is eclipsed. One star has eclipsed the another star. So at that particular time, when the second star is behind the main star, so that time you can call it as a epoch. It's called the epoch of that eclipsing system. A particular specific time where you want to say something interesting or something extraordinary. And a variable star, as the name suggests, it's a normal star, but it's not that normal because its brightness, it varies, and it can vary from a time scale from minutes to hours or even days. So, like in the previous notebook, I mentioned that we don't rely on the the universal time coordinate. Instead, we are interested in we have defined one particular unit, which is known as Julian date. So by definition, Julian date is the So by definition, Julian date is the continuous count of days since noon universal time on January 1, 4713 BC. So since it by definition Julian date starts on noon time. So which means that whenever we observe, so if we start observing during evening time, let's say 7 p.m., and if you observe till morning, let's say 6 a.m., so if you use Julian date, so you will have one Julian day, I mean, for the whole duration of observations. And because the UTC changes during midnight and the JD remains the same, so for simplicity, we are particularly interested in using Julian day whenever we want to emphasize on time series data. But here is a catch, because you see, we are so astronomers all around the world. They are observing with their own facilities, and we are observing from different locations. So um, we we do have the different time zones, and for consistency, so all are around, so that all our observations they appear as consistent, we use Julian date. But here's a catch. So because our earth is like rotating rotating um, around its axis, and it's also orbiting the sun. So because of that, might there is a slight delay in the time. The slight delay at the time, at the light which we are getting from a distant source. So for that reason, we have defined a uh, specific unit, which is known as the Barycentric Julian date. So here we consider that our solar system is at the center of the barycenter, and we just correct for that. And we use this barycentric Julian date in most of our observations. And now we will see how we can use Astropy time module for handling these various time formats. How we can convert the UTC date to barycentric Julian date, or the different, and between different formats. So these are the simple. So okay. So as we did last time in first tutorial, and you can go through this link and see what are all the time formats which Astropy can handle. So here we are defining our observation time as year, month, and date, and this is our minute and second, and we have defined that this is UTC, so it will give you something like that. So it will just give you an output containing that, okay, this is the UTC date of your observations. But we are not interested in UTC date. Most of the times whenever for consistency, we use Julian date. So we can just say that, okay, this is so here we have defined a Julian date, which is 2460265, because the 0 point for Julian date was January 1, 4713 BC. So it's these many days have elapsed from this date. So here, if you run, here we have just noted it down that, okay, our format is Julian date, and you can say it will give you an output containing that, okay, this is your Julian date. And because you see, this is very complicated, it's a very long number. So there is a simplified version of Julian date, which is known as the modified Julian date. And it just there is just an offset between Julian date and modified Julian date. So because you see, the modified Julian date it's still the noon time, and it's still the, it's just an offset between November 17, 1858 and this January 1, 4713. So here we have defined our MJD, which is the modified Julian date. And in a similar manner, you don't have to do anything fancy. You just have to call time and define whatever time you're interested in. And you just have to specify, okay, what format, and it will give you the whatever time format you are interested in. So here we have seen that you can call in UTC and in Julian date and in modified Julian date. You can also convert between these time formats. So suppose your entry was in UTC and you want to convert this entry, which was here in UTC, and you want to convert this entry to modified Julian date and Julian date. So you just have to provide the individual date formats you are interested in, and you can just call that entry. And if you just use .mjd, it will give you the result in modified Julian date. And if you use JD, it will give you the respective result in JD. So here you can see the same UTC time observation date in modified Julian date and Julian date. So now, suppose you are interested in, so you want to, suppose you have a particular time you have observed a celestial source, and you just want to add something to that observation time. So you can also perform these time, the arithmetic operations here. So you can define any entry here. You can say, okay, time 2, and time 2 is your observation time. And here you see we are interested in adding one day and 6 hours. So here when we are using this thing u dot day, so we are defining that this value is, its unit is day. And when we are saying, okay, unit dot hour, so we are defining here that, okay, whatever entry I have written here, it's in its unit is hour. So if you just add these two, it will give you something like this. So you see it has just added 1 day and 6 hours to our observation date. So our observation date was 15/11/2023 at 12 hour, and it has just add 1 day, which is 16, and just 6 hours to our observation time. So what I want to say that you can do all arithmetic operations here. And if you are interested in seeing the duration between the two observations, so you can also just do a subtraction between the two time events, like whatever time you are interested in. So you see here is just a simple thing. You have defined a new time here, and this is our observation time. And we have just used in simple arithmetic operation here and just printed the difference. And this difference is in days. And this is because now here we have defined the u dot hour. So this is telling us that now the difference is in, it will give us the result in hour unit. Now, this time module of Astropy, it can also handle arrays of different times, and you can also create a new array for your own observations, or a new array of any type of time data. So here we have defined a MJD array. These are just the MJD sequence, which is starting from 60264, and we are just adding point 0.1 in these sequences. So now if you would like to see these arrays, so because we have already defined here, and we have already defined an array for these MJDs, so we can call the time module here, and we can say that, okay, this is the array I'm interested in, and this is the sequence of modified Julian date values, and we can specify here, okay, my format is modified Julian date, and if I run it, I will see that, okay, this is my array which I have just created. Now you can also call individual entries from here, or if you want to see first entry, second entry, or any kind of entry, for that you have to just call this time array MJD, and you have to mention that, okay, it's the format is MJD, and it will just give you this result that that you were interested in second entry, and this is the result you have got. It's 60264.2, and this is the corresponding UTC value. Now, as we have discussed what a light curve is, so basically a light curve is it's kind of very fundamental tool whenever we are interested in time series data, and we are interested in how the shape of the light curve changes over a course of time, or as long as like over a course of our observing duration. So in a light curve, we have time in x-axis, which is the time of our observations. And as I said that, because for consistency and for simplicity, most we are interested in barycentric Julian date, and the y-axis, it represents the brightness or flux or magnitude. I mean, flux and magnitude are, I mean, they are just related. It's just that the flux is a linear scale and the magnitude is in the logarithmic scale. So now we will see some common light curve. I mean, we will see how light curve, any particular light curve looks like. And this exam, this will also tell you that, okay, how you can call uh, how you can call an online database, and if the data is already published and they have provided all the table containing the light curve data, so you can also call that table and see how the light curve looks like. So here we will see uh, the light curve of a microlensing event from Ogle. So Ogle stands for optical gravitational lensing experiment. So it is a planetary microlensing event, which is known as this Ogle 2019 BLG 1180. And more details about this event, or if you are interested in reading a paper about how they identified this event, you can go through these respective links. So this data was, because as I mentioned that this data was already published and is already available in an online database. So we will just query that database using the whatever modules we have in Astropy. So here we have just called astropy.table, and because we are interested in, because the data would be in a table format and we want to see that data, and this is the astroquery is it's a tool which is used to query astronomical database online. So we do have different kinds of database like Vizier, Simba, and NASA Exoplanet Archive. So here from astroquery.vizier, we are importing Vizier module so that we can access any catalog which is hosted on this Vizier service. Now, so if you go to this website, like if you're not interested in doing in like using Astropy, and if you go to their website, so there is a restriction on rows which can appear on the screen, And I think the restriction is about 50 or 100 rows. But here we have defined that, okay, we want to see all the database. So this specific line, row limit equal to -1, it tells Vizier to return all available rows from the catalog, because here we are interested in seeing the full database. And here in this command, so we have used get catalog, and we have already provided the reference to which, I mean, we are interested in. And this 0 tells us that, okay, we are interested in the first table on this paper. So this is a reference to a paper which is published in a journal, which is this AJ, which is for Astronomical journal, and these are the respective path to that journal. So now we do have our data from in this instance which we have defined, and this particular command, it will print the first 5 rows of the table. So see, this is how the data looks like. This is the instrument KMTA02, and these observations, they have denoted in heliocentric Julian date, and this is the magnitude, and this is the respective error of in that magnitude. Now, since so this time is in heliocentric Julian date. So heliocentric Julian date is slightly different from the barycentric Julian date. So in barycentric Julian date, we consider that our solar system is at the center of our barycenter is at this center of the solar system. But here, heliocentric means we are considering that, okay, sun is at the center of the solar system. So there is a tiny difference between heliocentric Julian date and barycentric Julian date. So now we are interested in plotting this data. So we want to see how, like, on which time scale we can see this type of variability. So even if you don't see the full data, you can just imagine that. Okay, so see here, the data starts at 19.00, then the second entry, it is 19.35. So there is already a difference of 0.35 magnitude. But since we have an associated error, so it's not very easy to say whether, this variability is real or not. But if you see the whole light curve, you will have an understanding that how much is the variability amplitude and how variable is the source. So here we have just defined a JD offset, because so you see this time is heliocentric Julian date, but there is an offset to this date, so which we have defined here. And so we want to make a time. So we want to make an array which represents our time array. So for that, we have just did this. We have defined an offset, and we have said that, okay, the format is JD, and it's just that this times we are seeing in JD, and we are applying the JD offset. And these are the usual command lines which you might probably know till, because we have, like, you are already familiar with the matplotlib package and how do we use the different routines. Like error bar is used for when we are interested in plotting the errors in the data, and these are all the basic stuff. And but the main point is that, okay, we have in this line, so we have provided the x value, which is time. And since this array contains all the information, and if you just call this array and you call I magnitude, so it means that it will basically take all these values because that's the header we have here, you see. And in the error we have just called ei magnitude, so it will consider all these values. So now you can run this cell and see how the light curve looks like. So this total duration, so it's almost 900 to almost 700 to 750 days of data, which you can see here. And see here, you can have a sense that, okay, this looks very constant. This doesn't look so much change here. But here you see between this time range, maybe I don't know. Okay, between this time range, you can see there is a spike. There is a spike in the magnitude range, and then again. So so magnitude has like so the magnitude has increased here, like so it has rebrightened, and then there is a sharp fall in the light curve. So you can see that this event, I mean, it's a transient event here, which shows a significant rise and then fall. And the typical magnitude difference between the quiescence level of the light curve is around 19.2 or 3, and then you can see it's 18.0 magnitude. So because flux and magnitude, they are like, so in magnitude scale, so whenever I say that, okay, 18 point, so we generally use magnitude scale like inverted. So when I say that, okay, 18.0, so 18.0 means my target has like it's brighter, and 19.5 means the target is faint. And yeah, so this is the light curve of that microlens event. Now, okay. Okay. Just give me a second. Sure. Okay, the second light curve which we are interested in is the center of our galaxy, Milky Way, and we are talking about the central black hole here. So we will use the same thing which we used here. I'm not able to. Let me just. Okay. So we are interested in the light curve of the central black hole of our galaxy Milky Way, and we will use the same routine which we used earlier. So it's like we are again using the widget catalog, and we are using the same function widget.get catalog. And now the part to our catalog is different from the earlier one. And in this instant also, we are interested in the first table, which is like which is published in this paper. And this makes sure that we are interested in only first 5 entries. So here you can see, okay, here you can see, so we have modified Julian date in time axis, and on I mean in for values now we have flux, and this is the corresponding error, the associated error with our flux values. Now we would like to see how this light curve looks like. So again, we are not doing anything very peculiar here. So we just defined offset here, which is like, so you see the starting point of MGD is 56636. So we have defined an offset in MGD time, which is 56. I mean, just the closest round number here, 56630. And we have saved this data as an array using so we have called that our X values are time values, which are the time we are interested in, the MGD, and minus the offset. So if you run this cell, you will see the light curve of Sagittarius A, and you see. So, okay, so now, so because here we have used the data from Spitzer Space Telescope and it operates in infrared band. So this, you can see this is the wavelength is, the central wavelength is 4.5 micrometer. And you can see how variable the target is. And there are sudden changes in the sudden rise and decline, just like the short-tooth wave, and then again it goes from 0 to 0.010. So this, you can, I mean, you cannot say if you can see any variability from this point to this point, but you can easily see that, okay, this is something which we are interested in. So this is just a very basic example of light curve data. So now, till now we talked about like infrared. How do I? Okay. So till now we were interested in seeing the infrared light curve and optical light curve. Now we will see a light curve which is observed in radio wavelength. And so the process, like the emission in radio wavelengths and in optical or IR wavelengths, the physical process is quite different. And you can read more about them, like, so this will be your task, that you must read about what is the synchrotron emission and what is the coherent emission and what are the physical processes of any astronomical object, and so that they emit in radio wavelengths. But I will just show you some examples of objects which astronomers are interested in studying in radio wavelengths, and they include pulsars, because pulsars are basically rotating neutron stars, and when they rotate, they emit beams in radio wavelengths. Similarly, ASEAN are also observed because they contain a supermassive black hole in the center. So and when any kind of ASEAN is observed in radio wavelengths, they also show some kind of flickering, or I mean some kind of variability, and which can go from months to years. And the fast radio bursts, these are also some mysterious, and they are very powerful or very brief duration of radio waves from any extragalactic sources. So here, we will use the same Visual database, and this is also a link to the paper which is already published. And if you want to read more about this paper, so you can go through this archive link here. So this source was observed in L band, which is 1.4 gigahertz, and we will just see how the data looks like. So you see here the first 5 rows of this data, where this is the time in JD and this is the time in, so this is the Y value, which is flux. So in radio wavelengths, mostly the data is stored in, the flux unit, which is a Jansky. And somewhere, I don't remember the correct conversion, but you must check, like it is something 1 Jansky is 10 to the power minus 34 watt per meter square per angstrom. It's something here. Okay, 10 to the power minus 26 watt per meter square per hertz. So whenever we talk about Jansky, so this is what we are talking about. So this is the same usual stuff. We are here, so because we already have the table header is JD and flux, so we are calling here the JD. We are interested in seeing we are just applying an offset to this observation time. So this is the first line which defines our time, and here the second line we are applying that offset which we have already defined, and this is just the plotting commands which we have used till now. So this is the x value, this is the y value, and because we don't have errors in our data set, so we will not include any errors here. And now we will see how this radial light curve of this particular target looks like. So you see, okay, you see this target is really variable on a short time scales, and if I remember correctly, so they have these people had shown that the variability of this time scale is just 6.5 minutes. So this means that the difference between this to this is just 6.5 minutes. So in 6.5 minute scales, it rises up and then it falls down and comes back to its normal state. Now we will see another light curve, which is from a variable star, which is known as RL Leo, and it's a and we are just now we are using a catalog. So this is this is the automated survey of this facility is used to detect for the detection of supernovae, but because they are also monitoring the sky, so they also publish a lots of variable stars using their data set. So here you can see this table, it's already here, and so we have just used Pandas read CSV module to read this table, and here we have defined that okay, this we are filtering out that data which has error greater than 1. So we are not interested in that data because 1 is quite a huge error. So now we are using head this command. So it will just give you the first 5 entries like we were using here. So where we were calling the first 5 rows. So here we can also use this command head, which will give you the first 5 entries of this table, the table which we have already downloaded and which we have stored here. So here you can see, so this SSSN has different cameras. So all these observations are from the same camera, but there might be some data which can be from different camera, but it doesn't make a difference. So this is the time in heliocentric Julian date, and this is the magnitude, error, flux, and flux error. So now we have here 5 entries. I'm not considering camera, but we have 5 entries for a time series data. We also have magnitude, and we also have its associated error. Then we have flux and the associated flux error. And okay, so if you do describe, so it will just give you the statistics of the data table. So it will just give you the mean value or the standard deviation, and what is the minimum value, what is the maximum value, and what is the median value. So it is very, I mean, it is very useful if you just want to have a look at the data and you want to see, okay, what is the minimum magnitude you are observing and what is the maximum magnitude you are interested in. So here you can see in this data, the minimum magnitude we have uh, which we have is 15.596 and the maximum is 16.942. So you get a sense of that this star could also be available because the magnitude difference is huge. So now we will use the standard matplotlib thing. So we will just define our time as, I mean, because we have already defined our data as our Leo, so we will just call HGD header and we will just apply an offset and we will just, I mean, it's just that time and that magnitude and so here we are only interested in the scatter plot, but here we are also defining the error bar because we do have information on its associated error. So you see now we will be able to see a variable light curve of this target RL Leo. And you see there are epochs, like when I say epoch, so it could refer to any specific time. So when I say that this epoch corresponds to the time when the star was observed in a faintest state. And here this epoch corresponds to that time when the star was observed in its the brightest state. So you see this light curve is very variable with the the difference in the magnitude is 1.4 magnitude. So this notebook, like, it provided an introduction to how to look a light curve from the published data set, and you must have a sense of how a light curve looks like. And whenever we say light curve, so what we are referring to, so it's basically the time in x-axis and flux or magnitude in y-axis. So you can use Astropy time objects to convert between different time scales, and you can use those time scales for plotting purposes using matplotlib library. So now we already we just like we have just seen the three different light curves, but the next notebook, it will demonstrate how we can query the light curve data from transiting exoplanet survey satellite. So it's called as TESS, and how can we find periodicity in this data. So for that, we will move to our next and final notebook. Okay, so the main objectives of this tutorial will be to understand time series data and to understand specifically the tests. We are mainly interested in test light curve data here, and how can we identify the periodic signals from the individual light curve, and what are the techniques which we use to find the periodic signals in the data. So as I have already discussed, like, what is a time series data, so you can just go through these things, and these are the different examples. Like the most common example of time series data could be the variable stars, because the variable stars are those which change their brightness over a course of time. It could be every night or it could be days as well. And for some objects, the variability time scale could be even hours or even minutes. And the second example is exoplanet. So it's like when a planet moves in front of its star. So because it's in front of the star, so it will block some of the light which is coming from the star. So because it's blocking, so you will see a tiny dip in the light curve. And if you analyze that dip in the light curve, you can discover, okay, it might be a new exoplanet. And I already discussed about pulsars, which are like the rotating or the rotating spinning neutron stars. And supernova, they are like, so supernova is the end stage of a star's life. So when a star explodes, it suddenly becomes very bright, but then slowly it fades away. So depending on the physical process, the duration between the brightening and fading away, it could be days or months. So right now in this tutorial, we will exploit test data, and we will specifically use this light curve package. And we will use this package to first accessing the data, and then like how we can access it and how we can download it, then and how can we plot that data, and then how can we identify any periodic signals in that particular data. So these are all the libraries which must be installed before running these tutorials. So if you want to read more about like what data products test gives, so you can go through a link I must have written somewhere down, so you can go through that, but I'm just like briefing it here. So the test the test provides two data products. So one is the light curve. So it will be just a table which will provide you all the necessary information a light curve should have, which should be time and then flux or its error, or magnitude or its error. But there is another thing, and which is known as target pixel file. So these are the stacks of images with pixel level observations, and it will have different. So I mean, you can use these target pixel file as well, and you can create a light curve from this as well. But right now we are only interested in the light curve products. So to access the light curve in the test database, we should have some prior information. Like we should know what is the test input catalog identifier, which is something like this, or we should know the coordinate of our system. So either we should have this tick identifier, or either we should have these coordinate, and any format will work, whether it's in decimal format or whether it's in hexadecimal format. So the Lightcup package is specifically made to access the data from TESS, Kepler, or Kepler-2. So in the below example, so we are interested in a target which is an eclipsing binary. So eclipsing binary means there are two stars, and they are orbiting around the common center of mass, and because of their temperature and the brightness of the individual stars, so it's like when one star is eclipsed around behind the second star, you will see a dip in the light curve. And similarly, depending on its size, you will see how the light curve will look like. So we are interested in Beta Persei, which is a very, very famous eclipsing binary star. So we have already imported light curve package as LK. So we will just use LK here, and there is an inbuilt module there, which is search light curve. So we will use this search light curve here, and we will specify, okay, which target we are interested in, and which mission we are interested in. And this author commands, it just tells us that, okay, the data we are interested in is it's the pipeline produced data. So this SPOC pipeline, it provides the 20-second or 120 seconds cadence data for tests. So whatever data we will see from now onwards, uh, so the difference between the two consecutive observations, it could be either 20 seconds or 120 seconds, which is equal to 2 minutes. So like in each data, so you are seeing the magnitude, I mean, you are getting the data point after every 2 minutes. So if you use this and you just print search results, you will see all the information. So this table tells you that, okay, this is the target, so this is the TIC number, and it says that, okay, the distance is 0, which means we are on the right target. And these are the different years and the different sectors. So the test observes a 24-degree cross 96-degree field of view, and then it shifts. So these 24 cross 96-degree field of view is known as a sector. So that's why the same target is observed in different sectors and in different year. So, and you see, this is the exposure time, and in one of the sectors, we have 20-second data and as well as 120-second data too. Okay, so now what if you don't know the target name, but you know its coordinates? So if you just write, I mean, you don't have to change many things. You just have to, in the target keyword, you just have to provide its coordinates, and you can also define the radius and mission, and all the remaining things could be same. So if you run it, you will see it will give you the same result. So you can query the test data based on the coordinates or based on the target name. Now, let's suppose you don't have any information about which sector it has been observed, but you just want to check, okay, whether a specific target is observed in a particular sector or not. So for that, you can also specify sector in this search in search.gov module. So you can also, I mean, so because these are 4 entries, and if you're only interested in the first entry, you can just mention a 0 in this search result, and it will give you the first index. So it will give you the first sector observations. Okay, so as I said, if you're interested in only in sector 18, but you just want to see whether this particular target beta per se is observed in sector 18 or not. So you specify all these things which are very common, like you specify mission, you specify, okay, you want a specific data product from SPOC pipeline, and you specifically mention, okay, that you are only interested in sector 18. So you can just run this cell, and this will also give you the same result. And if there have been multiple observations, like if there would have been a 20-second data, so you would also see that thing here. So, okay, let me just change this to, okay, 85, just for now. But we are not changing the name because it doesn't matter. Oh, it's okay. So here you can see. So if there are multiple exposure time observations, so you will also see those observations here. So right now we are only interested in sector 18 data, so we will move forward with that one. So this will be your exercise to search and download all other light curves. For now, we are only doing sector 18 light curves. So this will be your exercise to do to download and to plot the light curves from all other sectors, which are 58, 85, and I mean the both 20-second and 120-second data of 58 and 95. So how to download a single light curve? So to do that, so because to that we have just used this download package download module here, and because we have already identified our search result 18, which corresponds to sector 18 data. So if I define my light curve as search result 18.download, it will give me a table, an Astropy table containing all the related information. So it will give me time, flux, and time correction, cadence number, and all other related information. But the thing is that I'm not interested in all these other information, and I am only interested in the two values. So which is flux here, this flux, and its error. So I mean, there are different types of flux which test provides, and okay, this is a link where you can read more about like what is the difference between the target pixel file and the light curve file, and also what is the difference between this SAP flux or PDC SAP flux. So this SAP flux, it is the simple, I mean, this is like you are doing an aperture photometry around the target, and whatever flux you are seeing, this is that flux. So now we can examine, so now because we have this table containing all the information which we should have for a light curve data, so now we can just use this table. So here you can use the NaN values from your dataset and any outlier values using just this command, and we can plot our light curve. So I have just renamed it the clean light curve because I am removing NaN values and as well as the outliers values. And you see, so here this is the time, which is, so this is the barycentric Julian date, but it's there is some offset between, so BTJD means it's the truncated JD, I mean the for tests there is an offset between the JD date, and because you see it's starting from 1790, so there is an offset between Julian date and this value, so that's why they have written it as PTJD. It means that the barycentric Julian date, but in test format, so that offset must be around 2457000, but it doesn't matter because that is a constant offset and which have been applied here. So you see, this is the light curve of beta Persei, and as I said that this star is an eclipsing one, so you can see a dip here, and then when you see a dip here, and then it goes the normal, I mean it goes up, and then you can also see this small dip here. So now we are interested in seeing, okay, what is the period? Like, what is the period between these two dips, or let's say these two dips? So to find these periodicities, we will use another, we will use something which I will just let you know in a while. But before that, so we already have an information that it's beta, so its period is 2 days, 20 hours, and 49 minutes. So which we will confirm from our analysis in a while. But for ecliptic system, it is kind of easy because you have time information. So like you can note this time here, and you can also note the time here. And if you just take a difference of these two times, you will have an idea, okay, this is the variability time scale we are talking about. And if so, this is like if you want to save the data to your local machine, so you can just uh, create a new data frame, and you can define whatever values you want to save in that data frame. Here we have defined time, simple aperture photometry plugs and its error, then PDC save flux and its error. And we are saving all these columns to this data frame, and we are making a directory here. So this will be this directory, which will be here, and then after making it, we can just use it in your local machine, and you can just upload it anywhere you want. So in this manner, you can save this data, like this data, in a text format. Now, how can we find periodic signals in the light curve? So you see, in this type of light curve, there is a pattern, there is a repetitive pattern. So whenever there is a repetitive pattern, so it means that a period is associated with that pattern. So, but whenever an astronomer observes, we don't collect data at regular intervals. I mean, let's suppose I am interested in beta Persei and I am observing it from South Africa, but I cannot observe that target continuously, because since there would be a daytime as well, so I cannot continuously monitor the target from ground-based telescope continuously. The second thing is that the weather might be bad. It could be cloudy, rain, and high winds, and you cannot observe targets. You cannot operate telescope in these bad weather conditions. And there is something called visibility. So because our Earth is rotating, so there are some objects which we cannot see in certain seasons. So it also depends on that. And the second thing is that you cannot use a telescope to observe a single target, right? And even if there is something, it might be too expensive or it is too difficult to observe constantly. So my point is that the TESS is the space-based telescope, so it was quite easy there because we had the continuous data set. Like from here to here, we have continuous data set, and because even in space-based telescope, there is a thing where when it's at perigee or the data needs to be sent back to the Earth. So at that point of time, you cannot observe your targets. So that's why there is a gap even in this test data. But even if we exclude this gap, our data is continuous from here to here. So this total duration is 13 days, but it's possible from space-based telescope, but it's not possible from ground-based telescope. So we need some technique which can overcome this issue, like which can overcome this issue when we don't have the evenly spaced data. So that's called Lom's-Gargle periodogram. So this is the routine which was designed or illustrated by uh, these two scientists known as Lom and Scargill, and there is the reference to the paper which you can look into, and it tackles this problem where the data is not evenly spaced. But what do we need for it? So we need a data set which we already have, which contains times, and that which is not equally spaced. And if we are observing from ground, there is no chance that the data will be equally spaced, and we need values which are recorded at those times, like in brightness or magnitude, whatever. Now, how does this work? So it checks for different frequencies, and I mean, different frequencies which could be present in the data, and then it fits it fits the data with that frequency. So that's how this technique knows that, okay, this is the correct period for in your data set. So the output of this technique will be the another data set, but now because it's like we are going from time space to frequency space. So it's basically like Fourier transform, but the Fourier transform only deals with evenly spaced data. So there are some changes which have been done in the algorithm so that it can understand that, okay, the time is not uniform and the time can be unevenly spaced. So the output of this technique will be the data set containing frequency and power. So if any data set you will, so there will be multiple peaks, but the taller the peak, the stronger it's evidence that that particular frequency is present in the data set. So now we will use the Lumps-Gargle package, which is or an inbuilt Python package to calculate the periodogram for our data. And we have defined it as ls, and here is the Lumps-Gargle routine, which we are calling, and we are using. So the input is time and then flux, and we can also provide its error value. And here we are defining our frequency and power data set, which would be the output of this routine. And here we have specified one thing, which is the Nyquist factor, and which we have specified 1. So this Nyquist factor 1 means, so it's kind of the maximum frequency we can extract very correctly. And the maximum frequency, it depends on the sampling rate, which means, it depends on the duration between the two consecutive data points. So if your observations are happening in minute scale data, so you will see a comparatively larger value of maximum frequency compared to when we are observing in our scale data set. So now we will run this cell, and our frequency and power are already stored in these two arrays. And now we will use this cell just for the plotting purpose, where we are not doing anything very special. So we are plotting, and this is our x value, which is frequency, and this is our power. And we have specified our x limit to go from 0.1 to 1, and you see we can see a nice Lumps-Gargle periodogram of our data. So you see here, you can see two peaks, and this peak at almost 0.35, almost 0.35 is a little bit larger than the frequency at 0.75. You can also, if you want to know the exact value, you can define a parameter known as best frequency, and you can use the argument max module of numpy, and you can use, so it will give you that frequency which is associated with the maximum power. And for period, you can just divide, like the inverse of a frequency is period, right? So we can use the maximum argument of power to define our best frequency. And you see the best frequency is 0.3511 cycle per day, and the period is 2.8486 days, which matches quite well with the information we had. So it's like here in the literature, the value is 2.867, and we have got the value to be 8486. So this tells you that our analysis is correct. And now it will be your task to do the same analysis for other sectors and to see if there is any difference between the frequency or what. And you can also, I mean, and these are the references which you can have a look, and the this will be the some questions and for your project. And apart from, like I said, you have to run the same tutorial for the other sectors data as well. Okay, yeah. Thanks. This is all from my side. And yeah, if there are any questions, you can ask them here.
Good morning, Nikita.
Good morning.
Thanks for your presentation. And I just have a doubt. On the previous notebook, the second one, when we were defined, we are seeing the time series of the, for instance, the light curve. You define the offset. I would like to know what criteria do we use to define offset? We look to the values,
So
or you use the mean? Try to
no,
mean.
so you can just use a first point to define the integer value of first JD point. So okay, let me just share my screen again. You are talking about the second.
The second Jupiter.
Yeah. So okay, let's see this data set. Okay, this one. So here
Yes.
you can see the first point is 2458911.37. So this offset, it could be random. Like you can also say that the offset could be 2458900, or for simplicity, you can also say that, okay, the offset is 2458910, because you don't want to use this large number as like while plotting purposes, or for, I mean, when you want to do the periodogram analysis, this doesn't matter, because the difference between the times, it will be uniform even if you subtract the same number. So it's just that you can also subtract the first integer part of this value. So you can subtract 2458911 or 910 or 900. It's just for the simplicity and conciseness.
Then I have to see the first value and decide which value to consider, or I can use I can calculate the mean of the
No,
the.
not the mean. You cannot use the mean. Yeah, you can just use the first, I mean, the integer value of the first data point.
Okay, fine.
Yeah. Oh, so okay. So there is one question: how can we get data of observations done by tests which have not been analyzed yet? They are not catalogued or no paper has been written on them. Okay, so the third notebook which I presented here. So, okay, sorry, here. Okay, no, it's here, sorry. Here, so here, if you know that, so as I said, you should have an information about whether the source has been observed with tests or not. So even if you don't have that information, you should have an information on which target you are interested in or what are the coordinates. So you can just use this line, I mean this first line to search light curve module, and you can specify that you are interested in this mission. So this all data, it is quite possible that this data is published, but even if it is published, you can access the data from using the light curve package. So either you decide on the target name or you can put the array and tag of the coordinates, and if you query, you will see the light curve here. I mean, even if it's not published in any catalog, you can just query using the light curve package. Does it answer your question? Okay. So let me know if there are more questions or more doubts or anything. You can always put your questions on Slack, like after running all these tutorials.
Okay, thank you for this session.
Yeah.
I have a class to catch, so I'll probably have to hop off.
Okay, it's okay. Yeah, fine.
All right, everyone. Thanks, Nikita, for the presentation this morning. So, guys,
And
we'll
Daniel, we
reconvene.
will have the same session at 6, right?
Yes, the next section
Okay.
starts at so that's 4 p.m. UTC.
Okay, sure.
Late in the evening it's going to be the same presentation. So those who have joined this morning, there's no need for you to join in the evening. Also, the recordings will be available on YouTube. It's also streaming on YouTube, so you can go check that out in case you want some clarifications. I'm creating a new channel now on Slack for week 5. Please
Okay.
just go there and ask your questions, and you will see it now week 5 in the Slack channel, so that you can ask your questions, and then Nikita can also check out and give you feedback, or any of us can comment. Also, do not forget to check out the additional link in the notebook 3, the last link, notebook. There are a couple of links there that will also help you get started for how to additional examples, maybe things beyond what we have taught here, and also how to query LightGov data. The LightGov tutorial, they have tons of tutorial on their website. There's also ones for doing flare analysis. There are also ones for Stingray for high energy time series analysis. So again, thanks for joining us this morning. And again, do not forget to kickstart your capstone project. You can use the resources that you've learned so far to kickstart and do your analysis. If you have any questions, please do ask in the Slack channel. Thanks, everyone. Let's meet again in the evening. Bye.
Bye, everyone.
Bye.